Okay, so we are going to continue by talking about trapezoids and kites. So this kind of finishes out the special quadrilaterals. Last time in 6-4 we did parallelograms and all the special parallelograms, right? Rectangles, rhombuses, squares. What did I forget? Did I forget something? I guess just regular parallelograms and all the properties that went with that. So we had that pink sheet. Remember that pink sheet? So see if you can find that pink sheet again, because we're going to finish filling out the back of that with trapezoids and kites. So I want you to be able to have that pink sheet completely filled out so that it kind of becomes a study guide for you by the end of the unit. Okay, so I'm going to skip right down to the meat of the lesson here, where it says a trapezoid is a quadrilateral with exactly one pair of parallel sides. So on your pink sheet, you can go to trapezoid, and you're going to write down a quadrilateral as the definition, a quadrilateral with exactly one pair of parallel sides. So it's going to look like this. One pair of parallel sides, one pair of sides that are not parallel, because if the other set of sides were parallel, what would we have? A parallelogram. So a trapezoid is different. There can never be overlap between trapezoid and parallelogram. Okay, so in a trapezoid, if we look at naming, this is back on the white notes now, naming the parts of a trapezoid, you have the two parallel sides, and those are called the bases. And you have the two non-parallel sides, and those are called the legs. So if these two are the bases, that makes them parallel, we have what we call base angles. These two angles are base angles, and these two angles are base angles. Now, we don't have a relationship among them like congruent or anything else with regular trapezoids. We just are naming them in pairs. The top two touch the first base, so those are a pair of base angles, and the bottom two touch the other base, and so those are a pair of base angles. The only time you're going to have a relationship amongst those base angles is if you have this special type of trapezoid called an isosceles trapezoid. So just like isosceles triangle means two sides are congruent, same thing with isosceles trapezoid. Two sides are congruent, and it's going to be the two non-parallel sides. So by definition, an isosceles trapezoid is a trapezoid with the legs that are congruent. So in other words, the non-parallel sides are congruent. So on your pink sheet, you can add that definition. An isosceles trapezoid is a trapezoid with congruent legs. In other words, the non-parallel sides are congruent. Question for you. Can the parallel sides of a trapezoid ever be congruent? Why not? What would it be? Or just really even just a parallelogram. You could have, if the top and the bottom are congruent, it would be a parallelogram. So yes, it could be a square or a rectangle, but it wouldn't be a trapezoid. If the two parallel sides were congruent, it wouldn't be a trapezoid anymore. So the only choice to make something isosceles trapezoid, two sides congruent, it has to be the two non-parallel sides that are congruent. Okay, when you do that to a trapezoid, when you create a trapezoid where the two non-parallel sides are congruent, we get some special properties that happen. So these two things are going to happen. So again, on the pink sheet, if you finish, this is finished filling out the blanks for trapezoids. The two properties, each pair of base angles is congruent now in an isosceles trapezoid. So we're going to have this angle congruent to this angle. That pair of base angles is congruent. And then this bottom angle is congruent to this bottom angle. Again, that only happens when it's an isosceles trapezoid, not with regular trapezoids. But the other thing that happens is that diagonals are congruent. What was the other shape that had congruent diagonals? Diagonals. Rectangle, which includes squares also, right? But that's the other one that has congruent diagonals. Okay, let's go back to the white notes. Oops, that's not back to the white notes. Here we go. So the two properties that are listed here, each pair of base angles is congruent. The diagonals are congruent. Let me ask you this question. How does this angle and this angle relate? They're supplementary. Why? Same side interior angles. Very good. So you might want to make a little note of that here, right? This angle and this angle are supplementary. Is that true with isosceles trapezoid and regular trapezoids? Look at this diagram. Is this isosceles? Are these two angles going to still be supplementary? Are they still same side interior angles with parallel lines? Yeah, so they're still going to be supplementary. And these two angles will be supplementary. Okay, so something else about trapezoids. And this is not really a property. It's just another feature of a trapezoid that can help us find missing sides. And that is the mid-segment. The mid-segment of a trapezoid. So the mid-segment of a trapezoid is the segment that joins the midpoints of the two legs, so the two non-parallel sides. Take a midpoint of each and then connect them, and that's the mid-segment. Does that sound familiar? What else did we do mid-segments of? Triangles, right? So take the midpoint of this side and the midpoint of that side, connect them, and we had the mid-segment of a triangle. What do you remember about the mid-segment of a triangle? Good, it's half of that base, of that other side. Good, it's also parallel to that third side. So we said it's parallel, and we did 2 times the mid-segment. Remember doing that? 2 times the mid-segment equals the parallel side. Now, this is only in triangles, right? Mid-segment of triangles. How many mid-segments can a triangle have? Yeah, there were 3 that we could draw. 1, 2, 3. How many midsegments can a trapezoid have? Only 1. So there is a relationship similar to with triangles, but with a trapezoid, the midsegment of a trapezoid basically equals the average of the 2 bases. So if you have this diagram here, you've got a short leg, I'm sorry, not a short leg, a short base and a longer base, and then the midsegment is here in between. It's actually the average of those 2 lengths. So if the top one was 10 and the bottom one was 30, what would be in the middle? 20, because it's just exactly halfway in the middle. It kind of makes sense even in visually looking at it. So you can think about this formula as being the average of the 2 bases. Or you can think about it similar to when we did triangles. 2 times the midsegment equals B1 plus B2. It means the same thing, right? Taking B1 plus B2 and cutting it in half. It's the same thing as doing 2 times the midsegment equals B1 plus B2. Okay, so let's see the types of things we could figure out about trapezoids, right? If CDEF is an isosceles trapezoid, and the measured angle C is 65 degrees, what is the measure of angle D, E, and F? Measure of angle D is, what is it? 115. How'd you get that? Yeah, they're supplementary. What's the measure of angle E? Also 115. And the measure of angle F? 65. So this is all having to do with the properties of isosceles trapezoids. Base angles are congruent, and both sets of base angles are congruent. Okay, if C, D, E, F were not isosceles, would C and D still be supplementary? Yes, we talked about this already. Why? Because same side interior angles are always going to be supplementary if lines are parallel, right? Okay, so let's find some mid-segments here. Find the length of the missing segment. So they have a question mark there. I'm just going to call it X. So again, you can do the average of the 2 bases, 9 plus 13, and divide by 2. Or you can think about the formula as being 2 times the midsegment equals B1 plus B2. So 2 times X equals 9 plus 13. So 2X equals 22, and X is 11. With part B, yes, it's still the average, a little bit less straightforward if thinking about it as an average. So I'm going to stick with 2 times the midsegment. So 2 times 19 is the midsegment equals B1, 13 plus B2X. So what's X have to be? 25. Good. Okay, so you try number 4. Again, think about 2 times the midsegment equals b1 plus b2. Write your equation. Don't forget parentheses and so on. 2 times x plus 2 equals b1 plus b2, and x is 3. Any questions on that? Okay, so there's a couple more there to try, but I'm going to skip down to talking about a kite. So this is our last quadrilateral, special quadrilateral, is a kite. The definition sounds a little bit weird, and when you write it on your pink sheet, you're going to have to kind of abbreviate and don't write too big because you got to try to fit it in there. A quadrilateral, so a kite is a quadrilateral with 2 pairs of consecutive sides congruent. So you're on your pink sheet now. A quadrilateral with 2 pairs of consecutive sides congruent, but no opposite sides congruent. Okay, so 2 pairs of consecutive sides congruent and no opposite sides congruent. So what does that mean? That means that you've got 2 sides next to each other. Consecutive means one right after the other, that are congruent to each other. And then the other 2 sides are consecutive and congruent to each other. But they can't all 4 be the same, in other words, right? If opposite sides can't be congruent, that means they can't all 4 be the same. So with a kite, there's 2 special properties with kite. The first one is that the diagonals are perpendicular. So when you draw the 2 diagonals of a kite, they will intersect at right angles. And the other property, and I kind of changed this one a little bit. Instead of one diagonal, I put the longer diagonal. The longer diagonal, this one is longer, creates 2 congruent triangles. So you split it down that longer diagonal, and the top triangle and the bottom triangle, or left and right, depending on how it's drawn, are congruent. But here's another way of thinking about that. The longer diagonal is a reflection line. It's a line of symmetry. Everything that's created on the 2 sides of that longer diagonal are exactly the same as each other. Okay, so that pink sheet should be complete now. Let's go back to our other notes. And again, the 2 properties here, diagonals are perpendicular. What was the other shape that had perpendicular diagonals? Rhombus. Rhombus has perpendicular diagonals. So I kind of made a note of that. Sometimes it's good to make connections in your head there. And the longer diagonal creates 2 congruent triangles. Again, a good way of thinking about that is that the longer diagonal is a reflection line. So this triangle is exactly the same as this triangle. I like thinking of it as a reflection line because even if I draw in the other diagonal, everything's still reflected. So that means like this angle is the same as that angle. Right? Everything's reflected. This angle is congruent to that angle. This one is congruent to this one. Okay? Everything is reflected. Okay, so look at number 7. DEFG is a kite. What are the measures of angle 1, 2, and 3? Well, based on the special properties of a kite. What's the measure of angle 1? 90 degrees. Good. The next thing I can really find here is the measure of angle 3. What's measure of angle 3 going to be? 52, and that's because this longer diagonal is a reflection line. So if this angle up here is 52, that means angle 3 is 52. Now I can use angle sum to get measure of angle 2, which would be 38 degrees. Okay, you guys try number 8. Same idea. $6 degrees. And angle 2, 54 degrees. Okay, look at the back for a minute. On your pink sheet, you had a visual of the types of quadrilaterals as like a family tree. Let's just look at that really quickly. Right? Kind of like a tree diagram here of all of the categories. And now we're looking at this is another sort of visual way of depicting the different categories of quadrilaterals. It's a Venn diagram. The big box represents all quadrilaterals, all four-sided figures. We've got parallelograms in here, and inside parallelograms we've got rhombuses, rectangles, and squares. Those are all special types of parallelograms. Some parallelograms don't come in any of those categories, but they're still would be inside parallelograms. Remember that if a rhombus, if there's a shape that is considered a rhombus and a rectangle, that shape is a square. So the overlap here is where rhombuses and rectangles come together as a square. Trapezoids and kites are now what we added into this these categories. Notice that they don't intersect at all. Right? Trapezoids, kites, parallelograms do not intersect at all. Just like in the tree, there are 3 separate branches. You can't have, a parallelogram that is also a trapezoid. You can't have a kite that is also a parallelogram. It just doesn't work. They cannot, they're called mutually exclusive events. They cannot ever overlap. Well, this kind of a diagram, I think, helps with questions like these, sometimes, always, or never. So if you look at this Venn diagram and answer these questions, a rhombus is sometimes, always, or never a parallelogram. Always, because it's inside that category, right? Next one, a parallelogram is blank a rhombus. Sometimes a rhombus. A rectangle is sometimes a rhombus. When a rectangle's a rhombus, what's it called? A square is blank a rhombus. Always, because the whole category of squares is contained inside the rhombus, right? So always rhombus. A rhombus is sometimes a square, because only part of it is together. A rhombus is blank a hexagon. I hope that's an easy one. Never a hexagon, right? Okay, so you have a summative on Wednesday. It will cover 6.1 to 6.4, not 6.5. Okay, for homework, what I would like you to do is finish the 6.4 P2 practice that I gave you. And when I say finish, I mean, do as many problems as you feel get you ready for that summative. You might not have to do every single problem, but you should do more than just one of each section. That's not enough practice, all right? Also finish the 6.1 to 6.3 practice. You already did the evens. You should be finishing up the odds for homework. I would like you to try to finish this chart as well for homework. This little chart right here is just a bunch of check marks. You do not have to do the textbook pages. So the big thing to focus on is being ready for the summative. Okay.